All right, we're good. Bill starts off.
Objectives. After studying this unit, the reader will be able to explain the performance requirements of Article 250, explain how the performance requirements relate to the prescriptive requirements in the remainder of Article 250, explain the meaning of objectionable current over grounded or grounding conductors,
Okay, and take this next one.
explain proper connections of grounding and bonding equipment, explain the importance of providing clean surfaces for grounding and bonding connections.
I mean, I think we can all think about how important a clean connection is. We're just gonna be beating these raw, like as we go, so we might even skip by them. But let's talk about this. This is very important. What is objectable current in your own words? Does anybody read ahead, or did anybody read the book from last week? Right? In the best to your ability, describe objectable current.
So objectionable current is any current over equipment grounding conductors.
So put it into layman's terms. If you were to explain to somebody who had no electrical knowledge, how would you word objectionable current?
Current where it shouldn't be where it,
Yes.
you know what I mean?
Or neutral current flowing over ground,
Yeah.
or something like that. That's basically what we're dealing with there. Sorry guys, I'm just gonna be jumping ahead here, trying to get all of our important stuff. Finish.
Table 250.3 covers additional grounding and bonding requirements that are found in other articles. The rules in NEC chapters 1 through 4 apply generally. Rules in chapter 5, 6, and 7 can amend or supplement the rules in chapters 1 through 7. This provision is found in 90.3.
Alright, so please remember that, guys. The first 4 chapters are going to be general information, and then 5, 6, and 7 are going to amend anything before it, based on a set of specific qualifications. If it doesn't meet every single one of those qualifications, 9 times out of 10, it does not get an exemption. So the stuff that we're talking about is the bread and butter of grounding and bonding still.
The prescriptive methods contained in Article 250 are to be followed to comply with the performance requirements of this section. 250.4A1 gives examples of performance goal. No specific measurable requirements are provided.
Once again, we have our traditional system here. It shows a fault there. It's going to go back and it's going to get grounded out because that is going to be grounded. Ties back to that. That case is grounded. It's grounded to that case. It still meets through here, meets that case. This case is bound there, still jumps through to the main. The main is grounded. You know what I mean? Does it have a path? Is it bonded? Is it a complete? Is it an effective ground? If something happens here, could that effectively make it back to the next ground rod or all the way back to the circuit? Once again, we're going to be beating this raw. That's all we're talking about here.
Uh, 250.4 grounded systems. 250.4A provides performance rules for grounded systems. 250.4B provides performance rules for ungrounded systems.
Like I said before, they might say that systems are allowed to be grounded. If something says it's allowed to be, I consider it to be, this must be grounded. I'm always going to do over, in the last class I was mentioning this a lot, I always go over the code minimum. Code minimum is fine for somebody who just wanted to eke by and do the absolute minimum, but that's not me. I like the CYA. I like to cover my ass. Cover your ass, CYA. So always go a little above what's required. Take this again. There's a lot of slides.
Electrical system grounding. Electrical systems that are grounded are required to be connected to the earth in a way that will limit the voltage imposed by lighting, line surges, unintentional contact with higher voltage lines. Will stabilize the voltage of the system to earth during normal operation.
Does that all make sense to everybody? Any new crazy information found? No. Once again, any overflows, it's going to be dissipated into the earth if it's properly grounded. This is a typical system of what you'd see in your house. You have I always just call it 7K, but it can actually be considered 7.2K. What does that mean? Phil, when I say 7K, what am I talking about? Do I get like a new TV that I can see everything? It's in 7K. I can see whatever I want.
Isn't that the prefix just saying kilo, like
Oh,
kilo or kilo?
okay. So it's 72,000 or 7,200 volts rather. All right. So like anything that's supplied in your street, like they didn't come up with that number off the top of their head. That's usually the lowest voltage on the high side of that transformer. So coming down your street, usually it's 7,000 or 7K, 7,000 volts. And that transformer knocks it down from 7,000 to $120. And it's got your ground and neutral in the center. So if you go from line to that ground or to the neutral, it's going to give you 120. But if you go line to line, it's going to give you 240. That's the most common type of transformer system you will see in residence. That's residential. You don't see that in commercial applications. Like here, we're either going to have a wire or a delta system. This is what you'd see on your street. That lone bucket with one lone wire coming into it, that'll convert it to 240. Like I said, all of the overages is going to hit the earth. Some way, shape, or form it has to. And these are showing us our systems here. Ground and conductor, ground and conductor, ground and conductor. That means that neutral, when it comes right at the transformer, is grounded right then and there. If there's a transformer up on the pole, there's usually a wire coming down to hit the earth. It's got to be a grounded system. You'll see these two in industry. You'll only see this in residence. Any questions? We'll talk a lot more about transformers later. It's just crucial now that you know what they do, and they just step up or step down voltage. Nicole?
Grounding electrical equipment, normally non-grounded carrying conductive materials enclosing electrical.
Wait, I think you said it a little wrong. It was normally non-current carrying. I think you said non-ground carrying.
Oh,
I'm sorry.
Normally non-current carrying conductive materials enclosing electrical conductors or equipment or forming part of such equipment are required to be connected to earth to limit the voltage to ground on these materials.
Does that make sense, people? All they're saying there, if you got a metal object encasing that wire or something that wire is supported on, it should be grounded. You got the transformer, it's grounded. You got the panel box, it's grounded. And that neutral, like I said before, is grounded as well. So like I said, any bit of metal, you want to get it away to earth or an effective path to earth. You can have another panel box that's all the way over here. If you're in two lots, a neutral and a ground, if something happened, that ground is isolated, has a way of hitting this box, and it has a way of going to the earth. Okay? It's all about forming an effective path. Take this one again.
Grounding electrical equipment. A shock or electrocution hazard can occur if there is a break in the ground fault return path.
What is this called? I mentioned it before a lot in our first class. What's the big thing we're worried about? A difference of what? Potential, right? Because of the poor connection here, it might physically be touching, but it could be rust, it could be corrosion, it could be paint, it could be anything. There could be a physical air gap there. It could be rubbing on a plastic bushing. They could have used the wrong hardware. It could be anything. But this is not making continuity with this. So that circuit is never going to trip. If it's a single leg, it's never going to trip. It's just going to sit there and scream until some poor soul comes and touches it and then touches a piece of ground equipment. Now that return path is going through your heart and it's probably going to kill you. So that's what we're trying to eliminate, the difference of potential. That's why we're so focused on grounding and bonding, so everything has a nice effective path, a nice effective and reliable path back.
Bonding of electrical equipment. Normally non-current carrying conductive materials enclosing electrical conductors or equipment or forming part of such equipment are required to be connected together and to the electrical supply source in a manner that establishes an effective ground fault current path.
What is putting two different pieces of metal together called? Perfect. His unsure answer is, is correct, it's bonding. What would be grounding then? I put two pieces of metal together, they're bonded.
Yeah.
What's the grounding side of that? Define grounding to me.
To the earth.
The path back to the earth. You wanna take this one as well?
Bonding of electrical equipment. In its simplest form, bonding completes a path through which current can flow. Also keeps connected parts of the same potential, eliminates shock.
Okay, so once again, we're talking about potential. If all these pieces of metal are touching and they're bonded, they're nice and secure, there's no way that my two hands, like if my two hands are two separate pieces of metal, there's no way that these can get taken off. So that means if I have an arc problem here, it's gonna pass through my hand to be able to trip out that breaker because it can make it back to earth. There's never an instance that one could float hot and one could be still grounded and me make that issue. So once again, that's the whole aim of what we're trying to do. And in here, they have the grounded service conductor come in, right? And this could be considered its main panel area, right? You only do that when it comes in. The neutral is bonded right to the ground. That ground comes out. Once again, we have a neutral coming down through here. The neutral is also bonded here because this is a big disconnect, and a disconnect is just like a meter socket. So all this metal is touching. It is all of the same potential. There will never be an instance that if I light the corner of it up here, it's gonna trip that out. It's not just gonna let one box buzz hot. Colin?
Bonding jumpers, main bonding jumpers, system bonding jumpers, supplier side bonding jumpers on supplier side of the service in separate or a separately derived system. Equipment bonding jumpers on the load side of the service, bonding jumpers to metal piping systems and to structural metal frames or building.
Colin, what the hell is a bonding jumper? Fill me in. Can you describe that to me? When they say a bonding jumper, what are we talking about? Is there a guy doing like jump rope and his name is bonding? He's a great jumper.
It's pretty much anything that is bonding, say either the box that you're using to
Describe the jumper itself to me. Like when we talk about a jumper. Phil, what is a jumper?
Just jumping the,
I know what it does.
Yes.
But what is it? I think we might be getting confused on this.
you're just connecting the.
Can you go to like Freeman and say, give me a bonding jumper?
Water.
And they just hand you a like a one size fits all bonding jumper. Like, what is it? He said wire. And that's half right, sure. It could be a wire that's going into a rated fitting. It can be a wire that has two ends crimped on each side so they can go over a bolt, right? Could a bonding jumper be a flat piece of copper between 2 points? Sure it can. How about a flat piece of aluminum? Sure it can. So when they say bonding jumper, don't think of, oh, it's just a piece of wire. No, it could be anything. It's anything that allows an effective path, right? So just please, like right here, let me. Like right just in this picture, I can spot many grounding jumpers. There's one right there. It's probably a little piece of 4-gauge copper that goes from the end of that terminal adapter, and it goes onto a little terminal on the thing itself. This bonding jumper is going to a bushing with a thread stuck at the side. It's like a thread protector bushing, but it's a bonding bushing. It goes over, when you stick pipe into a box, does that pipe just go in there clean? No, there's a lock nut and there's some extra thread. Well, that spins onto the extra thread and it has a terminal screw on the side of it. So now you can bond that right to that. In panel boxes, it's super common for that bonding jumper to just be a flat piece of metal. You know what I mean? Or it could be a piece of steel, it could be whatever. As long as it's large enough to not melt when it's operating on an overcurrent type deal. Like let's talk about like a 200 amp service, right? You have 4 aught, and 2 aught coming in. 2 4-aughts are your hots, right? But the grounding wire for that is 4 gauge copper. Way fucking smaller. Why? How is that possible? Is that ground wire gonna be carrying current at all times?
No.
No, it's just gonna carry it once for a very short amount of time, right? Just as long as it takes for that breaker to open up. So it doesn't necessarily have to be the same size, it doesn't have to be, it just has to be adequate, is what we're looking for. It just has to be able to take that abuse for a second or 2, or until that main breaker opens up. So please just don't go thinking wire, it can be a lot of different things. Any questions on that? Feel you good on that?
Yeah.
Bonding jumpers required. Instances, loose lock nut connections.
Like I said before, that wire, you have the thread going into a box, the lock nut goes on it. Yeah, if you got that hand tight, yeah, it would definitely have a connection. But is that guaranteed? What's gonna happen in 10, 20, 30 years? Is that gonna get hit by a forklift? Is that gonna get sprayed with some water and start rusting? Is there gonna be a corrosion issue apart from rust? You know what I mean? So just protect yourself.
For conduit or cable connections to be painted enclosures. Service equipment enclosures. Around
Concentric and eccentric.
around concentric and eccentric knockouts. Around knockout reducing washers if suspect connection. Hazardous classified locations. Over 250 volts to ground.
So over 250 volts to ground. So if I'm on a 480 system, 483 phase, each line, so now let me back up a little bit. A 208 3-phase system, right, is gonna have 3 legs of 120. A leg of 120 to ground is gonna produce obviously 120. But 2 legs of 120 are gonna kiss and it's gonna give you 208. So conversely, on a 480 system, each leg of that is 277. There's 3 legs of 277. But when you put 2 legs together, it's gonna give you a 480. All right? So that means on a 480 system, each leg is gonna be 277. So does that qualify that every single thing in that system has to be way more overly secure and way more bonded than it was on a 208 3-phase system? Yeah, because each leg is gonna be over 250 volts to ground. Just a heads up to that. Like 3-phase 208 is very common because 120 is great. You can use it for lights, you can use it for receptacles. It's very convenient to use. And if you want to power something big, we have some 3-phase power there available. But why do people want that 480 system? What's so attractive about that 480 system? The higher the volts, the lower the what? What's that equation? If I'm pulling 1,000 watts at 120 volts, how many amps is that column? Feel free to pull out your calculator. If you don't know how to get this by now, we have issues.
Volt times amps is watts.
Hmm?
Volts times amps, that's watts, right?
Volts times amps?
Or would you?
Oh, yeah, that
you
would
get it
be,
the other way around?
yeah,
Just
I'm
divide-
trying to go for the other way around though. I have 1,000 watts.
So you're gonna divide by the volts.
0.8.
So what do you have?
What'd you say again was the?
1,000.
You have 1,000 watts,
uh,
and we're at 120 volts.
Oh, 0.8. It's 8.
8, okay. So now, conversely, let's say I have that same 1,000 watts, but now I'm on a 240 volt system. What happens to that amperage?
Goes down.
Goes way down, right? By half, right? So it's 4 amps. The higher the volts, the lower the amps, and you pay by the amp, or you pay by the watt. So it's gonna be a lot more attractive for a big commercial facility to have everything they can run on higher voltage. Namely, lights. Like we just said in the last class, lights are considered a continuous load. But think of when you go to the mall. think about their biggest power consumption. It's probably lights, right? Like air conditioning, heat, yeah, that could be a big component. But hospitals, malls, commercial facilities, warehouses, a huge chunk of their power is just in light. And if you can get that light on a 277 system versus a 120 volt system, now it's even more efficient, right? So it's common to see, you know, like a huge 480 panel in a warehouse doing most of the work. You know, maybe have like a 200 amp, 120 volt panel box just for receptacles, for computers, things of that nature. Because receptacles don't run on 277, right? You really don't want to have a transformer in your building if you can help it. It'd be a bit more efficient to get two separate services. So just understand that 250 volt number, as soon as you see 480, you know you have to do a way better job of grounding and bonding than you even do on a 208 three-phase system, just because the over 250 volts to ground. Everybody got that? That's a pretty important lesson. What do they mean by knockout reducing washers? Has anybody ever heard of that? Anybody seen that?
Like a donut connector?
Yes, explain to the class. What's a donut connector?
I don't know, like you punch like a 2-inch knockout in the panel, and then you have to like run like a 1-inch pipe to it.
Perfect. It's a little reducing washer, right? It's just enough to make that space a little tighter so that conduit can fit in. And now what he's saying, let me attempt to draw this. So here's your panel box, and right here, somebody took out, let's say, a 2-inch hole, but they messed up and the conduit had to be 1.5 inches, let's say. And normally that 1.5 inch conduit would be way too loose. What you can do is you can put a large donut on the bottom and on the top. And that's that washer that he's talking about. And that's gonna be an 1.5 inch hole in the center, but well over 2 inches wide on the outside. So if you just stick that pipe through there and put that lock nut on, it's gonna squeeze that all together, filling the hole and keeping the conduit firmly in place. But do we think with all that extra metal and all that extra BS, it's gonna be a nice firm connection there? Definitely not. That's when you want to use that thread bushing with the grounding screw on it to physically go with a bonding jumper to the panel box, giving you a way better connection than that loosey-goosey connection. So do we all get all this here? Is anybody confused on that bushing?
Uniform code.
How is that possible?
I don't know. It's Mr. Woodruff. I'll do that.
Sorry about that. Any questions here?
Bonding of electrically conductive metals. Normally non-current carrying electrically conductive materials that are likely to become energized are required to be connected together and to the electrical supply source to form effective ground fault current path.
All right, so now I was just toting how safe conduit is. Why are these likely to be energized? What the hell kind of classification is that? Is that insulting to conduit everywhere? Why is conduit likely to be energized?
Metallic and it's carrying active conductors. It's metallic and it's carrying current carrying conductors.
Hell yeah, good call. You know, I mean, we're pulling that wire through. Is there a chance they can get damaged? If debris or anything gets in that pipe before we pull it, is there a chance that that can cause damage? If somebody hits that pipe with a forklift, is there a chance that can cause damage? Is corrosion a possibility in all those fittings that can cause damage? Absolutely. So we're going to bond that pipe physically right to the box. And like I said, when you're over 250 volts, that's not even an option for you. That's a requirement.
Effective ground fault current path. Electrical equipment and other electrically conductive materials likely to become energized to be connected, bonded in a manner that is reliable, provides a circuit of low impedance. The conductor must be capable of safely carrying the maximum ground fault current likely to be imposed on it. The earth is not considered as an effective ground fault current path.
And like they say it again here, the conductor must be capable of carrying the safety maximum ground fault current. Like I said, it's not gonna be for an extended period of time, it's only gonna be for a second or two. It's only gotta make it for a second, so, like, I know for a fact, like 200 amp service, 4 gauge copper is gonna be adequate to ground and bond that. And that 4 gauge copper is probably a quarter of the size of the conductors that are coming in. But once again, it only has to last for like 2 seconds. And as we go, or when you look in the book, there's a scale that shows you the amount of power versus how long it's gonna take to trip a breaker on average. And that's basically what we hone our wire at. That's what we hold it up against. Take this one again.
Middle conduit becomes current carrying conductor when returning fault current to source. Single loose lock nut or loose or broken fitting can result in break and fault path.
How many times have I beat that dead so far? 3, 4, 5?
Effective ground fault current path. Ohmic value of low impedance path. Not.
Impedance. Oh,
Oh.
you gotta. Oh, yeah. Sorry.
I'll try again. Ohmic value of low impedance path not provided in NEC. Keep all circuit conductors, including ungrounded, grounded, and equipment grounded conductors together.
Like I just said in the last class, it's a requirement that everything on that same circuit has to be together. You can't have 3 pieces of conduit and say, well, I'll put 2 hunts on this one, I'll put 2 hunts on that one. If they're all going to the same circuit, they all have to be in that same conductor. Or not in the same conductor, in the same piece of conduit. Okay, we all get that? I know it might be tempting, but please do not.
Most overcurrent devices, operating characteristics of overcurrent devices. Most overcurrent devices, such as circuit breakers and fuses, are inverse time. This means the greater the current that flows through the overcurrent device, the faster the operation will happen. Manufacturers furnish time current curves for the overcurrent devices they manufacture.
And that's the scale I was just talking about. Phil, in your own words, put that down to human speak for me. Put that down to basics.
So
If you were explaining this to a 6-year-old,
depending on the overcurrent device, depending on how much current is flowing through the return or the grounded system will trip the breaker faster than what if there's less current.
it's not over the ground system, it's over the breaker itself, right? So
Yeah.
like I said, we're not supposed to encroach 80% of what a breaker can handle in the efforts of keeping it cool. Because a breaker will trip on the combination of heat and current, right? The more current, the more heat builds, the faster it's gonna trip. And in that scale, let's say like, it'll say like 1, 1.5, 2, that takes up a great width of it, because if you're hitting a 20 amp breaker with like 1.1 times what it should be carrying, right? So it can carry 20 amps, let's say we're at 21 amps. Is that gonna kick instantly? Probably not. Because a breaker has to give you a little bit of time, it has a little bit of tolerance to it. Like if you turn on the vacuum, if you already have like a coffee pot going, and you turn on the vacuum cleaner, you probably dipped over that 20 for just a split second, and then it came back down to like a 19 level, like a 19 amp level. So it gives you it has a little bit of flex to it. Whereas if you took that same 20 amp breaker and you shot up to 40 amps really quick, it would probably pop it instantly. That's what they mean by inverse. The greater the current you're passing over that, the quicker it's gonna trip. So if it's just barely squeaking over what it should, it might run for a minute, 2 minutes at like 1.1. But if we're going 3, 4, 5 times what that breaker should handle, it's gonna trip instantly. So please remember, that's what they mean by inverse time. Now, inverse time becomes really freaking important when you're doing motor control, because we have thermal overloads and they only trip because of heat. So inverse time is what we deal with to figure out how much time it's gonna give us if we have like a high power current situation. So please understand this. It's not gonna help so much now, but next semester it's gonna help a lot. But just remember, if you're just pushing a hair over what that breaker was gonna take, it might take 30 seconds for it to pop. But if you're going many times over, like many times over what that breaker should handle, it's gonna pop instantly. That's like when a dead short, have you ever guys heard of like a dead short here or Freeman? You hear the brrr for like 2 seconds and then it turns off. Anybody ever hear a breaker turn off? Anybody ever see like a ground out? Normally it doesn't kill the breaker instantly. It still hums for like a second before it pops. So just understand that's what inverse time means. Anybody have any questions about inverse time? No? Where were we? Are you on?
Operating characteristics of circuit breakers. Vertical line in time current curve represents instantaneous trip current. Curved portion represents time delay mode of circuit breaker. Width of curve represents the permitted range of time delay in instantaneous trip operation.
Let me see this. What a way to find this if we can open it. So yes, page 48. That's exactly what we're talking about there. 48 and 49. But that's the skill that we're talking about. If you look at the very top, you'll see 1.1. But once it screams up to like 3-4 times its intended ampacity, it trips almost instantly. And that's the curve. That's how we size our grounding conductors. Based off of that, we know on average how long it's going to take for a breaker to pop. We know how long that wire is going to have to withstand that heat. We know the temperature rating of the insulation on the wire, so we can come up with a proper arrangement to figure out what size conductor we need. That's the nice thing about electrical, it's all science, it's all proven down to the quantum level. There's no BS, there's no, I think this, it's proven, it's a science. Any questions on that scale? Okay. And there's the scale here. Past that. Who's up? Nicole?
Operating characteristics of circuit breakers. Time in seconds on the left axis, multiples of rated current on the bottom axis. Every manufacturer can furnish time/current curve for each product.
And take this one.
Operating characteristics of fuses. Time in seconds on the left, RMS symmetrical current across the bottom.
Symmetrical.
Yeah, symmetrical. 60 amp fuse will clear in about 0.1 seconds to 400th amperage volt.
So, and then once again, it's noting the same thing. Fuses are like the same side of a different coin. Normally they're just instant. There are time delay fuses that do offer an element of flex, kind of like breakers, but normally they're pretty rigid. And that goes, if you were to hit that 60 amp fuse with like 62 amps of power, it'd probably run for a couple seconds. But if you hit it with 400 amps of power, it trips almost immediately. That's the ratio, that inverse ratio. And then when they say will clear, what do they mean by that? Will clear. They're saying that about fuses, and they're saying that about breakers. Will clear the circuit. What do they mean by that?
Cut power.
Yeah, that breaker opens up.
Yeah.
Right, it doesn't close. Closed is its normal operating position. When it opens up, can power pass between my hands? No. So when we mean to clear, to break, to open, that's what we're talking about.
Do fuses burn out though, or are those like, do they, right?
99% of fuses, yes.
Okay.
There are just a couple that we deal with in motor control that can heal themselves magically, but they're very few and far between, and they're very expensive. So yeah, fuses are a one-type deal. Fuse is actually the safest system in the world. Believe it or not, a fuse is actually a lot safer and a lot more reliable than a breaker will ever be. But what's the ultimate issue with a fuse?
That's what that means.
Your downtime. You're feeling around down the basement steps in the dark to replace a fuse in the middle of the night. You know what I mean? It's complete and utter lack of user friendability and all that jazz. They're just tough to work with, and they're expensive. They're a recurring part that you have to pay for every single time. And if you're dealing with like a 400 amp fuse and that pops, you're talking probably like a $200-300 fuse. Just one use, gone.
Do circuit breakers get bad over time though, like if they keep tripping? Like over-
Great question. What do we think?
Like, yeah.
Yeah? He says, you know, ask that question one more time so everybody can hear it.
So over time, if the breaker keeps tripping, will it lose its rating over time? Just,
And the answer is yes. It won't lose its rating. It's still
Yeah.
gonna say 20 amps on it.
yeah.
But between me, you, and the fridge, this is what we're talking about. So, yes, when I hear it in grounding and bonding in the lab, like it actually hurts my soul. I hear the click, 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 click of everybody hitting their breakers. Because yeah, like you're just used to it. You just start clicking it. Every time you hit that, you're weakening it. Just a little bit. Like maybe by like 0.001 amps every time. It'll trip a little earlier, not later, earlier. So after years of you hitting that breaker, instead of it tripping at 20 amps, it might trip at 19. You know what I mean? But I've been in a lot of factories and a lot of warehouses, EBSCO namely, all of their lights were off of breakers. Because once again, they had 277 coming in, it was just a big commercial warehouse. Who wants switches? Just go to that one breaker box and hit the first 5 breakers on the right. And I worked there for 3 or 4 years, and I know for a fact, just by feel, that my last week there, they're way easier to push over and turn on than they were when I started. The breakers have become weaker. You know what I mean? So if they tripped at 20, they were probably tripping at 16, 17. They're getting into the nuisance breaker realm. You know what I mean? Just like tripping way low for no reason. What's a way that we can get around that though? Is there a cure, Nicole?
Replacing it,
With?
a new one.
But that's the same problem's gonna happen. Like, granted, it'll take a couple of years, but the same problem will happen. If you have a breaker that you turn on and off frequently for common use, get a switch rated breaker. That breaker is now rated to become an overcurrent device and a switch. And you doing this a million times isn't gonna affect its ampacity. So, food for thought. But in most factories, you'll never see that. You know what I mean? It's only if that breaker should ever be a light switch. And to be honest, you really shouldn't have that either. But just food for thought. But yeah, even like a big blow, like my mom's famous for it. Every summer, this happens. She's cutting the hedges, and all of a sudden, poof, she'll hit that wire. That's right on the hedge clipper. Happens every summer. And she's done that so many times on the same fucking outlet, they've already had to replace that breaker. Because at a certain point when you just plug in anything, it just starts tripping because it's had so many big blasts of power that had to trip so many times. A big trip will weaken the hell out of a breaker. I've seen trips break a breaker. The breaker's just fucking put its life down and sacrifice itself for the good of the circuit. I've seen that many times. So, yes, they do get weaker, and yes, they do fail. They will kind of sacrifice themselves, much like a fuse. But by and large, if your issue isn't that great and it just kicks on heat, you can reuse that for a long time. Does that answer your question?
Yep.
Where were we?
I'll read. Keep all circuit conductors together, required in 250.1342 and 300.3 B1 through B4.
Yes, we all know those. Right
Yeah.
off the top of our heart, yeah.
Low impedance of fault return path will ensure adequate current will flow to provide for rapid operation of overcurrent device. See
Right.
white paper report of R.K. Kaufman in Appendix A of book.
How many times have I beat this horse dead? 5, 6, 7, 8 times now? Okay, we got something good here. Give me something good. Tell me something good here.
Effective ground fault current path. The conductor must be capable of safely carrying the maximum fault current likely to be imposed on it. Table 250.102C1 or 12.5% roll used on the line side of the service. Table 250.122 used on the load side of the service. Fault return path through the earth not permitted as sole path.
And as you'll read, what they just needed to hear about the 12.5% rule is, like on the line side of that, if the wire is starting to get too big to come up with an accurate number, you can just take 12.5% of the total volume of wire there, and that'll be sufficient for your ground. Okay, so like when the wires start getting big, like if you have 3 wires coming in, and they're within that conduit, right? You just do math and figure out the surface area of all 3 of those, and then just get 12.5% of that, and that's good for your grounding conductor. Because like I said, that ground is only gonna be energized for a second or two. You know what I mean? So it just has to take the brunt of that. It honestly just has to not melt. If we're just beating around the bush here. The wire just can't melt, catch fire, explode, rip in half. It just can't do that. But it's only gonna last 2 seconds. You know what I mean? It's like this belt buckle at the end of Thanksgiving dinner. It's only gonna last for 2 seconds until you go to the bathroom. So. I'll tell you what, I thought I was gonna get a chuckle out of that one. A little disappointed.
Like the ground fall current path. Fall current will flow over the paths available, including the dirt. Lowest impedance path will carry the most current. The highest impedance path will carry the lowest current.
So when people say that electricity takes the path of least resistance, I hate that. I hate that. People take the path of least resistance. Electricity takes all available paths. Now, the lowest impedance will carry the most current, but there will be current anywhere there is an issue. So please understand, if you have a couple ground rods, not just the closest one is gonna be getting power, they're all gonna be getting some form of power. Electricity takes all available paths. Might not be even, but it will take everything you've got. Okay, any questions on that? How are we looking at the time? What we got?
We've been at this for 41 minutes.
Okay.
11:25.
Okay, take this slide, Colin.
Bonding of electrical equipment. First ground fall on ungrounded system simply connects the system to ground.
Whoa, okay. So this is crazy, an ungrounded system. Let's see what this next slide has to offer. All right, now let's chat about it here. So there's only a couple systems and a couple reasons why you would want an ungrounded system. Phil, any ideas? Well, what kind of a system would prefer to be ungrounded? Why in the hell would you want an ungrounded system? I just told you about all the benefits. I made it clear that it's the right thing to do. Now, why do you want to not do that?
It's like, I'm thinking like communications or something like that, maybe like
I'm sorry?
communications or something like that, like, or like sensitive equipment.
Yeah, but there's also things that are not so sensitive, like motor control, all right? If you, let's say that, like conduit, right, it's likely to be energized because there could be potential issues. And if you hook that conduit up to an electric motor, there's gonna be a lot of vibration, a lot of nonsense, so it's even more likely for shit to hit the fan, correct?
Yep.
Is that correct? Now, if you were a facility like AZEC, right, and one of their machines goes down for an hour, how much money do you think they're losing?
6 figures.
After a day, yeah, they can be losing $100,000 in a day, just if one machine is down for a couple hours. You know what I mean? And then think of all the time it takes to start that machine back up, get all the plastic melters, get everything heated up, get the belts moving at a certain pace. If there is a ground fault on one, or like if one of these hits ground and it's an ungrounded system, that breaker will continue to run. Everything there will continue to run. What's common, there's gonna be alarms on every leg. So if an alarm senses that a leg has made its way to ground, it's gonna scream, yo, we have an issue over here. And electricians are gonna come over, find the issue, and fix it while the machine is running. Crazy. That's what we can do. That's why we make the big bucks. But there's only a few instances that an ungrounded system could be beneficial, and that is one of them, to keep production going, especially if only one leg hits ground. If 2 leg hits ground, then there's gonna be an arc flash and arc blast, and boom, that's gonna kill whatever breaker, you know, it's gonna kill the breaker. But this, if 1 out of 3 legs hits the ground, it gives you an opportunity to still have that equipment running. But now, if you were to walk up and touch that piece of conduit and touch another piece of conduit that was grounded, what's gonna happen?
Yeah.
You're gonna get lit on. So there's a big risk, but that's a risk and reward type of deal. And the guys who are working at that are gonna be authorized, they're gonna be qualified, so they're gonna be safe to work on it because they've been trained to work in those exact situations. Just so we all know. Who's up?
Bonding of electrical equipment. Non-current carrying conductive materials enclosing electrical conductors or equipment, or forming part of such equipment are required to be connected together into the supply system grounded equipment in a manner that creates a low impedance path for ground fault current that is capable of carrying the maximum fault current likely to be imposed on.
How many times have we talked about this? 12, 13, 14 times now? We're just beating the horse around. Take this one.
Second ground fault at different location on an ungrounded system. Current will flow from the source to the first fault over metal paths to the second fault and return to the source.
So what they're saying there is, like I said, we're gonna be dealing with that ungrounded system again. And now 2 shorts have occurred. Now it's gonna be able to kill the breaker. Because now we have a line-to-line short, the breaker's not gonna like that. But, like I said, going back to that single line, if just 1 leg is touching that, it almost feels no issue. You know what I mean? It's not using up any more power really. You know what I mean? It's just kind of flowing there. But if you put alarms on it, you can know that, hey, we had a ground out, somebody go and take care, it looks like it's line 2. You can go and assess that, you know. You can still do that while the system's running, which I think is crazy, but yeah. There's a lot of different, there's a lot more electricity out there than I even touch. You know, I'm a light commercial, residential, light industrial kind of fellow. You guys might be doing things completely different, so we have to be educated to experience anything. We don't know where our crystal ball is going to take us.
250.4B3, bonding of electrically conductive materials and other equipment. Electrically conductive materials that are likely to become energized are required to be bonded to create a permanent low impedance path for fault current that will carry the maximum fault current likely to be imposed.
Any new information there? No. I'm just double checking from my own sanity. Phil, say it.
Path for fault current. Low impedance path required from any point on the wiring system to facilitate the operation of overcurrent devices should a second fault occur. Earth not permitted as sole only equipment grounding conductor. Earth not considered an effective fault current path.
So what do they mean by those last 2 dots, Phil?
It's high impedance, it won't flow, it might take other routes other than going back to the earth.
Yes, but what they're saying, it's not the only, it's not
Yeah.
the sole. So on every system, what are 2 ways that power is getting back? It's going to ground. We know that. But what's the ultimate way of getting back to utility? Neutral, right? But that neutral has been grounded twice. It's been grounded at the transformer, and it's been grounded at your house. So once again, that earth is not the only one, but it's one of many, all right? Do we understand that? A little faux pas of information there? This is my favorite one. All right, hit me. This is we're getting some good stuff here.
Objectionable current. Term objectionable current not defined, so the term is subject to varying interpretations. Equipment grounding conductors are not designed to carry current on a regular basis. These conductors are often sized on their short time current rating.
Okay, now this is starting to bring together everything we've been talking about. We're beating the horse for a purpose now. What are they trying to get with here? You have been hitting Phil enough. You explain to me. What are they trying to get at there? Why is our ground not designed to carry loads?
Because the breaker's gonna break the current.
Will help them out?
It's because it's not supposed to be a carrying current conductor, so it's not meant to be used as like a full time. It's only supposed to be a temporary burst.
temporary
just, yeah,
large burst of power.
yeah,
But that's exactly right. Like I said, these conductors are often sized in their short time current rating, which is like what I was talking about. On a 200 amp service, we only need 4 gauge copper to handle all that. But it's only gonna get zapped for 2 seconds. It's just gotta not melt for 2 seconds. So objectionable current is that neutral current flowing back on the ground.
as the neutral would.
And it shouldn't be. The neutral should just be on its own white neutral line. Okay? So the objectionable current just means, in layman's terms, power where you don't want it is going somewhere that you really don't want it. You know, namely, neutral power. 9 times out of 10, we're talking about neutral power. Neutral power going off of the ground, which is what I was talking about with those smart devices. Why do you have to have neutral at every single pole switch? For that reason, because a lot of guys were going on the ground for that neutral. Did it still work? Hell yeah. But it was adding current to that system that need not be there. So that's objectionable current. Any questions on objectionable current? Who's up?
The arrangement to prevent objectionable current. The grounding of electrical systems, circuit conductors, surge arresters, surge protective devices, and conductive normally non-current carrying metal parts of equipment is required to be installed and arranged in a manner that will prevent objectionable current.
Yeah, all that means is just to not put neutral current onto the ground. Have your ground and your neutral terminals be isolated from each other on a sub panel. That's all it means, isolation. Want to continue?
Improper grounding of neutral past the service causes normal neutral current to flow on metallic pads. This is considered objectionable current.
So what you see here is they messed up hard. They don't have a ground going back through this, right? I think they're just maybe relying on that metallic raceway, but that's not even a good ground either. I don't see any bonding jumpers, I don't see anything. So all the neutral current is flowing, all the neutral and ground are flowing off of here into there, causing power where you don't want it. No ground. Everybody get that? And these are safe ways to prevent that from happening. Like I said, everything is nice and bonded and grounded. In our main panel, it's the same, it's the service coming in. So we have our ground and neutral in the same one. Yeah, that's a violation. I was just gonna say, why is that there? So on the main panel, the ground and the neutral are bonded, but on the sub panel, the neutral is isolated from that. Here they have, you know, like, I know you're getting into the habit of you seeing a neutral, seeing a ground, all right, let's bond them. No, you're only bonding them in the main panel. The sub panel has to remain isolated to keep that injectable current down. And what they did here is correct. Everything is bonded, it's going back to the grounding bars. Grounding bars are going to the ground rods, and only in the main panel, the ground wire and the neutral then meet there, and there alone. Okay, so that's the course of action. Do I tie the neutral and the ground together in a sub panel?
No.
Do I tie the neutral and the ground together on a main panel? Why? I figured just make you sweat it out, but it's code. You have to. It's required to give the lowest impedance and to give that neutral flow way back to the earth and back to the utilities. Like I said, you need more than one.
Like a bonding screw?
No, I said why.
No,
But could you do it with a grounding screw? Hell yeah.
like in the main panel, putting the bonding screw in,
Yes, because what does that bonding screw do?
ground and neutral, right?
How? Explain it to me.
Connected like the neutral bars or whatever to the box is connected to the little ground bar.
And it's all bonded. And it's all with metal touching. Perfect. Perfect explanation. All right, who's up?
Alterations to stop objectionable current. If the use of multiple grounding connections results in objectionable current, take one or more of the following actions. Discontinue one or more, but not all of the grounding connections.
Once again, you could have put the ground and the neutral together in a sub panel causing that, so that's what they mean by that. Continue.
Change the locations of the grounding connections.
And that kind of bleeds into number one.
Interrupt the continuity of the connector or conductive path interconnecting the grounding connections. Other remedial action.
Remedial. And what they mean by that is anything the inspector basically tells you to do. Hey, do it this way. Okay, buddy, you got it. You wanna take this one as well?
Current over grounding conductors. Neutral current can flow over equipment grounding conductors that are connected correctly where multiple grounding electrode connections are made. Neutral current will flow over paths that are available. This includes between grounding electrodes to the service and to the utility grounding electrodes.
Yeah, so that's why you just can't give yourself one ground rod and you're not connected to the neutral on the street. You need a couple paths to go, and it's gonna take all of them. Not equally, but it will take all available paths, okay? Any questions on that? I think you're allowed to have 6 disconnects in parallel. And because they're before your panel box, everything before and up to that main panel box is grounded and bonded together. And that's exactly what they're doing here. They have a ground rod going there, 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 there. And all the grounds are together. But that neutral is just bonded at that first one. To keep that impedance down here nice and low. Understand? Are you guys sick of hearing me talk yet? I'm sure you are. Go.
Temporary currents resulting from accidental conditions such as ground fault currents that occur only while the grounding conductors are performing their intended protective functions are not classified as objectionable current.
Let's explain that, Nicole. What does that mean in real speak, in real words?
So things that happen by accident with the ground fault are not classified as objectionable current.
Beautiful. Couldn't have said any better myself. And she's exactly right. Just because you have that one instance, right? Somebody might be metering, oh, we have injectable current. No, we just have a failure down the line. Try it again.
Limitations to permissible alterations. Alterations are not permitted to isolate electronic equipment from equipment grounding conductor path. Currents that introduce data errors are not classified as objectionable.
Yeah, data centers are an animal all to themselves, and they have a whole specific line of codes for them. And I'm gonna be honest with you guys, I don't deal with that shit often at all, so I know very little about it, and I can't even give a good enough argument as to what we're doing there. So please go by what the book has to tell you for this. That is, I have many specialties, and that is not one of them.
Limitations to permissible alterations. Not permitted to isolate data, processing equipment, and connect a local grounding electrode.
What do they mean by that? What does that sentence mean?
I barely understood it, and I read it.
So not permitted to isolate data processing equipment and connect a local grounding electrode. Seems to me that they're talking about if you have a dirty ground and the system's acting a little funky, you can't take it off the existing grounding system, drive in your own grounding rod, and just attach it solely to that, right? It still has to be bonded to everything. Yeah, well, like this is gonna say if you want to complete that.
To do so, violations 250.50, 250.110, and 250.134, and create shock hazard.
So Phil, like you just mentioned before, it's just like that light post we were talking about. You know what I mean? Like in the first slide, the first week, we were talking about that light post out, it had the ground rod right to the earth, and it was hooked right to it, and there was still a code violation. How is that possible? Well, that was grounded, but it wasn't bonded to everything else that was in that system. Continue.
A remote grounding electrode will usually not carry enough current to operate a 15 ampere circuit breaker.
So what they're saying here, and you can go on YouTube, it's true. If I hook up a 15 amp breaker and I have one side going right to ground, just to a ground rod, not bonded, because if that was bonded, it would blow out a breaker instantly, because it's letting all that power get back to the panel box. If I just hook up a 15 amp breaker and I have it connected right from the panel box to a wire that went to a ground rod directly into the earth, the breaker will just sit there and hum. There won't be enough power to dissipate it. Because it has to let those huge voltage spikes hit the ground. But a lot of bulk of that power is heading back on the neutral to the utility. So like I said, that's why you just can't do one. There has to be many paths for that power to take, because it's gonna take all available paths. Now, if you had 3 ground rods there, yeah, it'd be enough to blow that. You'd probably get 555, enough to pop it. But one ground rod by itself can't dissipate a lot of amperage. It only dissipates huge voltage spikes. That's really what that ground rod's for. Colin, are you up?
I believe so. Connection of grounding and bonding equipment. Equipment grounding conductors, grounding electrode conductors, and bonding jumpers must be connected by one or more of the following methods. Listed pressure connectors.
What do you think a pressure connector could be? When they say a pressure connector, what are they talking about? Do you just have to play like under pressure when you're hooking it up and now it's a pressure connector? You know what I mean? Nothing? Nothing, guys? Come on. I thought that was gold. Freddie Mercury? No? Anybody? No.
Yeah, we know who he is. We got the joke, I think, sir.
It was funny! Alright, come on. What do they do with pressure connectors? Is a set screw providing pressure on a wire that you put between the screw and the base of that fitting? Yeah, so it's just a screw fitting. It's just a fancy way of saying pressure. Terminal bars, like what you see inside the panel box, is grounding bridge, which is pretty much the same thing as a terminal bar. Pressure connectors listed as grounding and bonding equipment. Exothermic welding process, physically welding it, solder. Please will find out solder isn't a great idea. Continue.
Connection of grounding and bonding equipment. Connection methods. Machine screw type fasteners that engage not less than 2 threads in the enclosure or are secured with a nut.
I just talked about that, right? You can't use sheet metal screws, even though it's nice and tight. There still has to be at least 2 threads going through the material. All right. So if what you're going through is a 1/16 of an inch thick, you need 1/32 screws at least. Okay. Continue.
Thread forming machine screws that engage not less than 2 threads in the enclosure. Connections that are a part of a listed assembly, other listed means.
And by listed assembly, they just mean something that came from the manufacturer and that object is rated to carry that amount of flow. It's just not commercially available. And this is getting into those fittings here. Crimp is a big one. I don't know if they have it here. Wire nuts, terminal bars, grounding bridge, acorn connector, that's where you hook onto your ground rod. That's what hooks the wire up to it. Exothermic welding process, it could be solder, machine head screws, self-tapping screws, connections that are already part of your panel box itself, or other buses and crimp styles. Who wants to take it?
Exothermic welding process. Use proper form for conductors and objects. Follow manufacturer's instructions. Welding temperature reaches about 4,000 degrees Fahrenheit. Follow safety procedures. Examine and test finished weld.
Alright, now welding is fine, but I want to see if they talk about, yes. Okay, continue.
Compression connectors. Suitability for wire material marked on shipping carton or connector itself. Some connectors are pre-filled with an inhibitor.
What they mean by pre-fill with an inhibitor, like all the bugs that we use when we hook up our services, has a little dab of either the terminal paste I was talking about last class, or it could just be like a silicone, just something to prevent water and air from getting there and oxidizing. So it's just, you know, it could be oil, it could be anything, just to prevent oxidation or corrosion. Continue.
Connectors are designed and marked for a range of conductor sizes. Select proper compression tool. Some manufacturers use color coding, dyes, and connectors.
Yeah, it's common, like, I know like for like the smaller ones, they might say 20 to 16 right on the bottom of the hook. And that just means they can just accept between the gauges of 20 and 16. You know, pretty common sense kind of things. And that's a crimping tool. You just put your wire in there, put the crimping tool over that, and just literally crushes that metal onto the pipe with thousands of pounds of force. So now that wire can't go anywhere. You can get hydraulic ones, you can get hand ones. They all accomplish the exact same goal. Okay? Well, let's find out why solder is not allowed.
As is not permitted. Connection devices that depend solely only on solder are not permitted. Soldered connections can fail due to heating as they carry fault current. Also see 250.148E for restrictions on the use of solder for connecting equipment grounding conductors.
It's just solder. You don't have to pronounce the L. Or that's how I pronounce it, being a North Scrantonian. Either. But yeah, you can't use solder for a grounding system. Why? It says heat, but why? How is solder applied to that wire to begin with?
Heat.
By heating up the wire. So that flux or whatever you're using, that bonding metal, could instantly just melt away the second it gets into trouble. It only has to make it a second or two. But if it melts after a half a second, then what good is that fitting? So solder fittings are never allowed in grounding systems. Ever, ever, ever. Ever, 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 ever. Who's up?
Ground clamp, protection of ground clamps and fittings. Ground clamps and other fittings exposed to physical damage are required to be enclosed in metal, wood, or equivalent protective covering. Connections to ground rods that are above grade are particularly susceptible to damage and should be protected.
That's a loaded question. I've done it both. I've had ground rods that come up to the ground and they're just like, 4 inches proud. I've also been with people that want them buried, like 4 inches below dirt. Dirt is going to cause corrosion and all that jazz, but it's actually going to protect the wire from physical damage. Like you're not going to be able to hit it with a lawnmower. Like nobody's going to be kicking it. You're not going to hit it with a snow shovel. So what I do, and they definitely mention in the book, but Schedule 80 PVC with a cap, that's a great thing to just toss over it. It keeps that nice and accessible, so if you ever have to add ground onto it, or if you want to test that ground system, it's just as simple as taking the cap off, and that ground rod's right there. I also see that done commonly for like water meters, or like the gas meters. Anybody live in the city limits, and they have that old turn head in their yard or in their sidewalk? One says water, one says gas. They're about that big.
Really how they shut it off.
Yeah. Curb stop. Looks like that. It's gonna say water or gas on it. It's just got 2 little holes. I do that all the time with those, because what's gonna happen after a year or 2? You just put in your new gas or your water service. That fitting is sitting nice and flush in your grass. It looks great. What's gonna happen in 2 or 3 years?
Hit it with a lawnmower.
You'll hit it with a lawnmower, and odds are it's gonna get buried at some point. The grass will move, and then when shit really hits the fan, you have to turn that off. Where is it? I don't know. We have a problem. So it's nice to put that cap over because it's always visible. It's always there for you. I do that for like I said, the water and gas. I do it for ground rods, well points, external drain lines, anything that can be buried or hurt. Throw a little cap over it, protect it in some way, shape, or form. What's up?
Clean surfaces, non-conductive coatings, paint, lacquer, and enamel to be removed from threads and other contact surfaces to provide good electrical continuity. connection by means of fittings designed to make such removal unnecessary. No fittings are listed for this purpose. Paint is an insulator.
Yeah, which I don't even like that. I wouldn't view paint as anything. You know what I mean? That can get scratched off so easily. Don't think that paint is helping anything ever. If anything, in my humble opinion, that paint is just hurting you. You know what I mean? Because by the time all those panel boxes, all the square D panel boxes, they're all painted. You know what I mean? So if you just went to go and put a piece of conduit in there and just attach it via that, it would not be a good connection just based on that paint alone. Paint screws me 9 times out of 10. So do whatever you have to do. Get paint thinner, get an abrasive wheel, get some sandpaper, get something to scuff it up nice. And you know, the only time I like paint is to prevent future corrosion. So if you did all that, you sprayed it with spray paint, at least I know it can't really rust inside there. The paint isn't technically helping the connection, but it's preventing corrosion from forming in the future. So it's kind of like a double-edged sword. But just know that that paint, anything, has to come off. It has to be clean. It's got to be shiny. You know what I mean? Like this is trouble we're talking about here.
Two general forms: cut, punch from flat stock, crown threaded, tabs bent and left sharp. Cast from iron, aluminum, zinc, or other materials, may have relatively flat contact surfaces.
Yeah, and these are just lock nuts that they're talking about here. And when they say cut or punched, you can go with the hole saw and visibly cut out a hole, or you can go with a step bit, drill out like a 1/2 inch hole, and you can go with one of our hydraulic presses. It actually sends a post. Through that wall. You put a blade on one side and a cup on the other. And when you pressure that pump, it actually squeezes the two together and forces that tooth through the metal, creating a nice perfect hole. You guys will be doing punches when we start doing the service installation for that, but just know that that's what they're talking about there. Finish it off.
Summary: how the performance goals of 250.4 relate to the prescriptive rules and the remainder of Article 250. Requirements about objectionable currents over grounding conductors. Connection rules for grounding and bonding equipment, ensuring clean surfaces for connections.
Any questions? All right, Nicole, you can stop the video there because I'm already losing you guys.